Hi everybody. Today I am going to discuss about simply supported beam with cantilever overhang. Here come cantilever overhang means this part and simply supported on two supports having uniformly distributed loads, that is 4 kilonewton per meters. As well, it has concentrated load 6 kilonewton at the tip of the beam. Now, if we look at this structure, we can see at two supports there are two reactions. We need to find the value of these reactions. So, using vertical equilibrium or summation of vertical forces, I mean summation of Fy equal to 0. Using these equations, we cannot find these two reactions because two reactions are unknown. So, in this situation, a better approach is to use moment equations. So, what to do in case of moment equations? We have to take moments about B. So, automatically we are eliminating one reactions RB. So, easily we can find RA. So, this is the situations. RA into 4, 4 into 5 into 1.5, because this distance from here, this 4 into 5, this force acting somewhere here, 1.5 back of these supports, and this 6 into 1. So automatically we get RA equal to 6. It is kilonewton. Now, from vertical equilibrium, now we can use summation of Fy because already we know one force, I mean one reactions. So using this Ra plus Rb as well 4 into 5, this load downwards negative and as well this concentrated load negative. So we get Rb equal to 20 kilonewtons. So these two loads I marked it here, Ra equal to 6 kilonewton, Rb equal to 20 kilonewtons. Now the support reactions at B, it produces a loading discontinuity at B, so that we must consider the shear force and bending moments at two arbitrary sections of the beam, that is x1 for AB and x2 for BC. That is why I am taking a free body diagram of this one. From AB, I am taking this part AX1. And in positive directions, it has here in this side, I mean at this section, there is shear force and bending moment, mx1 bending moment, and this is shear force. So for this side, x2c, for x2c, I can take the free body diagram like the previous one, and it will be like this, having shear force Sx2 and bending moment mx2. Now I have to look at this. AX1 of this beam, we have to use vertical equilibrium. It means summation of vertical forces equal to 0. It means this one, Fy, summation of Fy equal to 0. So what it comes? Sx1 minus 4x plus 6. If you look at this, it's very clear. Sx1 minus 4 into x plus of this 6. So it is very easy to understand. Now easily we can write Sx1 equal to 4x minus 6. Now we have to apply boundary conditions. What is that? At x equal to 0, if you put here x value 0, Sx1 equal to minus 6 kilonewton. I mean it is at this position A. Again, another boundary condition, at x equal to 4, I get Sx1 equal to 10 kilonewton. It is here at B. Now, here one important point is, I know that this is minus 6, here it is 10. So, in between, somewhere there will be 0. So, how to find it? Consider this shear force equal to 0. So 4x minus 6 equal to 0. Easily we can find x equal to 6 by 4. So equal to 3 by 2, it means 1.5 meter. So from this end, 1.5 meter right, somewhere here, our shear force will be 0. So when we will see the shear force diagram, that time it will be very clear to us. So let's move ahead. Here I have to take the vertical equilibrium of length x to c. This one. What it will be? Sx2 4 into 5 minus x plus 6. Very easy to understand because Sx2 already it is here. There is a 6 here and 4 into 5 minus x equal to 0. So easily we can solve for Sx2 equal to 4x minus 26. Now we have to apply boundary conditions. Say for at B x equal to 4. So what will come? 4 means 16 minus 26, so it is coming minus 10 kilonewtons. Again, at C, I mean at the tip of this beam, if I apply 5, 20 minus 26, so it will be minus 6 at this point. So already we got shear force at all necessary points. Now we will concentrate on bending moments. So bending moment mx1, it is on this ax1. So what we can write, if we take moment about x1 at this point, moment about this point, surely it comes as this because this is concentrated moments. So mx1 will be as it is plus 4x into x by 2, half in the center it is working. So 4x into x by 2 minus of this 6 into x. So easily we can solve mx1. So this is the equation 6x minus 2x square. These equations actually it is parabolic function of x. Once we make the bending moment diagram, it will be very clear to us also. But seeing this, we understand that it is a parabolic function of x. So let's move in the next slide. So we brought this equation, parabolic function of x. Now what we can write? Here also, putting boundary condition, what we find? X equal to 0, it means moment also will be 0 at A, I mean at these points. Again, at B, if I put the value x equal to 4, so surely it will come x4 1632 minus 24, so it is coming minus 8 kilonewton meters. Now this equation we can write as this way also, taking x factor x into 6 minus 2x. It has some benefits. What is that? So easily we can say if x equal to 0, moment will be 0, or if this equal to 0, moment will be 0. So this is first boundary conditions. Again another boundary condition, if x equal to 3, it means if this 0 means 6, 2x equal to 6, so x will be 3. That's what it is. So mx 0, it means at x equal to 3. So what we found here, from here right up to x equal to 3, somewhere here our moment will be 0. And this moment 0, it is a significant points in a sense that we call this point of contrafluxure, because at this point the bending moment, I mean from here 3 meter far, at this point bending moment changes sign, the curvature of beam is 0. It is point of contrafluxure or point of inflections. So we'll see it when we will sketch the bending moment diagram, then it will be more clear to us. Now differentiating this equation, we find this dmx1 by dx equal to 6 minus 4x. So what is the benefit of this? If we put this derivative equal to 0, it means slope 0. Slope is 0 because it is at x equal to 1.5, because if you look at, if you 0, then x equal to 6 by 4, so surely it is 1.5. Now we can find at 1.5 distance what is the moment actually. At 1.5 the moment will be 4.5 kilonewton meters, because our moment at 3 meter it is 0. Here it is 3 meter, it is 0. As well here at A equal to 0. So within this 3 meter, in the center 1.5 meter far, our moment, sagging moment will be 4.5 kilonewton meters. So later we will see in the diagram. Here already we know this, at 1.5 moment is 4.5. So what we will do here? We will think of about some ranges. say x less than 1.5 and greater than 0. It is what? X less than 5 greater than 0. Here it says this decreases with x. While for x greater than 1.5 but less than 4 meter, slope increases negatively with x. So within this range means somewhere here, because 3 meter moment will be 0. So in between this, I mean from here to up to 1.5 meter, as curve will be like this. So here it says decreases, slope decreases, and here at the bottom sagging points it will be 0. Again after that it is increasing negatively with x. So we will see it in diagram also, and it will be very clear to us that time. So here bending moment mx2. Now we are thinking about mx2. Before we thought about mx1. Now mx2 means it is x to c. So taking moment about this x2, what we get? This is the equation we get. Because mx2, this one, concentrated moments, 4 into 5 minus x. 4 into 5 minus x. This is the load downwards. And it will work at the center. Center means 5 minus x by 2. So automatically it comes as this. Plus 6 into 5 minus x. So easily we can solve mx2. This is the equations. Now if we put boundary conditions, what it comes? mx2 minus h kilonewton meter at x equal to 4. Because if we put x equal to 4, it is minus 8 kilonewton meter. Exactly here. Right hand side exactly on the supports. At 4. mx2 equal to 0 at x equal to 5. I mean at the tip. Using these equations. Here it is, moment is 0. But in between this, nowhere slope is 0. It is very important points. Nowhere slope is 0 in the curve. That is why it says derivative is not equal to 0 at any point in BC. Because we put x equal to 5, it is 0. X equal to 4, it is minus 8. So from here minus 8 to 0. So in between nowhere slope is 0. Because this slope decreases as x increases. From here slope decreases like this as x increases. So it will be very clear when we will see the diagram. Next slide we will see that. Let's move ahead. So this is our structure. I brought all the shear forces at different points of the beam. So according to this value, I sketched this one, shear force diagram. Now we can explain this. You can see here x equal to 0 means minus 6 here. X equal to 4 means 10 here. X equal to 1.5, already I told shear force will be 0 here. Look at it is 0. And x equal to 4, sx2 minus 10, this one. For right hand side, this one. and at C it is -6. So we got full shear force diagram with the magnitudes as well with the sign. Now let's move for bending moment diagram. This is the value we got in previous slides. So now I will draw the bending moment diagram. What it says. Already I told at 3 meter it will be 0. This is actually point of contraflexure. This point, it is called point of contraflexure or point of inflection, because bending moment changes the sign. Here it is positive, here it is negative. So it changes the sign at point of contraflexure or point of inflections. And another important thing, x equal to 1.5, already we discussed before, x equal to 1.5. Here we got 4.5 kilonewton meter, this moment. And this moment, you look at exactly here, shear force is 0. Here moment is like, if we use W L square by 8, exactly same moment we got here, because slope here equal to 0. W means 4 into 1.5, I mean this is 3. So 4 into 3 square, 4 into 9 divided by 8, you will get this value. But we got this value using the equation in previous slides. So I think it's clear now. And as well here, I got for mx1 I got -8. Here from this direction it reaches here -8. Again for mx2 -8, from here it starts from -8. That -8 we got here at x equal to 4. But at x equal to 5 we got mx2 equal to 0. So it's very clear now, seeing the shear force diagram and bending moment diagram. That's all for today, and thanks for watching.